You know, when you look at a modern microchip, it's so easy to just see this flat, featureless little square of silicon.
Right, just a shiny black box.
Exactly. But if you actually zoomed in, like way, way in, what you were really looking at is a microscopic skyscraper. We are talking about 3D integrated circuits, where floors upon floors of processing power are just stacked directly on top of each other.
It's wild to think about. It really is an architectural marvel
It really is. But that marvel raises a pretty massive question. What happens when the tiny elevators connecting all those floors break?
because they absolutely do break
Yeah.
all the time.
Yeah, and the wild part is when they do break, the chip automatically heals itself. So, welcome to the deep dive. Today, we are exploring this invisible world of microscopic auto healing for you, our listener.
It's a fantastic topic.
We're pulling apart some really fascinating 2026 research by the researcher Luck036. The deck is titled Spare TSV Assignment via Cycle-Cancellation Descent. And it exposes not just how the self-healing works, but, how a single flaw in the underlying math can just bring the whole skyscraper crashing down.
Yeah, it really is a phenomenal piece of engineering to unpack those elevators you mentioned. They are the absolute lifeline of any stacked chip.
The technical term is through silicon bias, right?
Exactly, yeah. Through silicon vias or TSVs. They're basically physical vertical copper connections that allow data to flow up and down between the different layers of the silicon.
Okay, so just literal copper pipes.
Pretty much. But the problem is that punching millions of these microscopic vertical tunnels through fragile silicon wafers is it's an incredibly complex manufacturing process.
I can imagine.
Yeah, and because of that complexity, these TSVs are highly susceptible to manufacturing defects. I mean, literally a single speck of dust in the clean room can wipe out a whole neighborhood of them.
A speck of dust. Wow. So how do they deal with that?
Well, hardware designers do something very clever. They overbuild. They intentionally include these things called spare TSVs or STSVs.
Because they just sit there.
Yeah, they sit completely dormant, just waiting to step in and repair the faulty functional ones when things go wrong.
Okay, so a functional TSV fails a test and the system just reroutes the signal over to a spare. At first glance, I mean, that sounds like a straightforward detour, right?
It does sound simple, yeah.
But looking through the source material, there is this massive bottleneck hanging over the whole process. And it all basically comes down to, well, the speed of light.
Right. It comes down to strict electrical timing.
Because it takes time for the signal to physically move sideways.
Exactly. When a via fails and that electrical signal has to take a horizontal detour to find a spare elevator, that physical detour takes extra nanoseconds.
Which doesn't sound like a lot to us, but for a computer.
Oh, it's an eternity. If you're listening to this deep dive on a smartphone right now, the processor in your hand is operating on incredibly tight, synchronized clock cycles. Timing is quite literally everything.
So there's a hard speed limit.
Yes. This detour distance absolutely cannot exceed a strict timing budget, which the researchers mathematically define as Dmax.
Dmax, okay. And if the signal arrives, say, even a fraction of a nanosecond too late.
If it misses that clock cycle, the whole chip could crash.
Man. So the data just becomes garbage.
Total garbage.
Yeah.
So the central challenge we are looking at today isn't just about finding one spare. It's about how an automated system assigns thousands of spare TSVs to thousands of broken ones simultaneously.
Right, because you can't just fix one. You have to fix all of them without crossing wires.
Exactly. And you have to do it in a way that minimizes the total rerouting wire length across the entire microscopic skyscraper.
Okay, so to fix a physical problem on that scale, I mean, you can't just have a technician going in with microscopic tweezers. You have to turn the physical architecture into a mathematical puzzle, right?
Yes, you need a map that a computer algorithm can actually read and manipulate.
And the researcher accomplishes this by translating the physical chip into a graph model. Let's talk about that.
Yeah, it's a very elegant model. Think of it as a virtual network of nodes and connecting lines, which we call edges.
Okay, so nodes and edges.
Right. The broken functional TSVs are mapped out as primal nodes. In the language of the math, they are assigned a demand of -1.
Okay, let me make sure I'm visualizing this correctly. By a demand of -1, we mean they have one unit of data flow, like a supply that desperately needs to go somewhere.
Yes.
They are essentially the bursting pipes in our city's plumbing system.
That is a perfect way to look at it.
Yeah.
They are the sources of the problem. Then the spare TSVs are modeled as transit nodes.
And they have a demand of 0, right?
Correct. A demand of 0. They don't generate any data themselves. They are just empty pipes waiting to pass a signal along.
Okay, bursting pipes, empty pipes, and where does it all go?
Finally, all of this rerouted data flow mathematically empties into a virtual supersync.
A super sync, I love that name.
It's very descriptive. This supersync collects all the rerouted signals and carries a demand of n, with n representing the total number of faults on the chip.
Okay, so we have the bursting standard pipes, the empty backup pipes, and the main reservoir collecting all the flow. But what about the connections between them?
The edges.
Right, how does the algorithm know which pipes are even allowed to connect to each other?
Well, that is exactly where the DMAX timing budget comes back in. The mathematical edges, the lines connecting our nodes in the graph, they only exist if a spare TSV is physically close enough to a broken one.
Close enough to not violate that strict timing limit.
Exactly.
Yeah.
If it's too far away, the algorithm isn't even allowed to see it as an option. It literally doesn't exist in the math.
Oh, wow. Okay. And for the edges that do exist, the cost of using them, which is the edge weight, is calculated using a very specific formula in the deck.
Yeah, it's the floor of the physical distance multiplied by 100.
Right. Mathematically written as the floor function of the distance between O and V times 100. I noticed that in the notes, and it really made me wonder.
Why they did it that way.
Yeah. Why the floor of the distance times 100? Like, why not just use the exact physical distance, like 1.25 micrometers?
It is actually a brilliant trick for computational efficiency.
Really? How so?
Well, computers process whole integers vastly faster than they process floating point decimals.
Oh, okay. So decimals slow things down.
Considerably. If your distance is 1.25 micrometers, multiplying by 100 gives you 125.
Which is a clean integer.
Exactly.
Hmm.
And taking the floor just chops off any trailing insignificant decimal dust. It translates physical wire length directly into a mathematically pristine penalty.
So the algorithm can process it at lightning speed without, rounding errors creeping in.
Precisely. Keeps the math perfectly clean.
I love that. It's such a tiny detail, but it shows how you really have to adapt physics to work with a computer's brain.
You really do.
But, I do have to push back on one of the foundational rules in the source here. The model dictates that each spare TSV can serve at most one broken functional TSV.
Right. The one-to-one rule.
Yeah. Going back to my plumbing analogy, if a backup pipe is wide enough, why can't it handle multiple streams of water? If a spare has the electrical capacity, why is it strictly locked into this one-to-one relationship?
That points right to the critical difference between abstract graph theory and the messy reality of physical hardware.
Because in pure math, you could just change the capacity.
Oh,
Right?
absolutely. In math, you absolutely could route multiple flow units through a single transit node. You just give it a capacity of 2 or 3,
Yeah.
the math wouldn't care at all.
But physically,
Physically, we are not routing water. We are routing electrical voltage that represents distinct, highly sensitive data streams.
so if you push two separate signals into one copper wire, they don't just share the space politely.
No, they corrupt each other instantly. It would be like trying to have two completely separate conversations on the exact same analog phone line at the exact same time.
Oh man, so the result isn't two conversations, it's just noise.
Just static noise. So, to preserve data integrity, the mathematical constraint demands that each non-sync node can only have one outgoing flow edge. A spare can only host one guest.
Okay, that makes perfect sense. The math has to respect the physics. So we have our mapped out plumbing system, our integer-based distances, and our strict one-to-one data integrity rules.
The stage is set.
Now we have to actually solve the puzzle. How does the chip find the absolute most efficient detours across thousands of broken elevators automatically?
The mechanism they use is an algorithm called min-cost flow via cycle-cancellation descent.
Cycle-cancellation descent. I mean, even just the name sounds heavy.
It's a mouthful, for sure. This is the engine of the self-healing process.
If I'm a listener trying to wrap my head around this, where does this algorithm even start? I mean, it can't just guess the perfect layout on the first try.
Oh, no, it doesn't even try to be perfect at first. It essentially starts with a really sloppy first draft.
A sloppy first draft.
Yeah, the algorithm uses a basic breadth-first search to just find any feasible flow.
Okay, so just connecting pipes however it can.
Right. It looks at a broken TSV and grabs the nearest available spare over and over until all the broken signals have a path.
But it's obeying the rules, right?
Yes, it obeys the DMAX speed limit and the one-to-one rule, but the overall layout will be incredibly inefficient. Lines crossing, long detours, It's a total mess, but it's a functioning mess.
It's like paving dirt paths just to make sure the roads connect before you figure out where the actual highways should go.
Exactly.
Go.
Then, based on that sloppy first draft, the algorithm builds what is called a residual graph. And this is where the real magic happens.
Okay, a residual graph. What does that do?
In this residual graph, the algorithm goes hunting for negative cost cycles.
Negative cost cycles.
Yes. When it finds one of these cycles, it pushes flow through it to cancel it out. And it repeats this process on a continuous loop, finding negative cycles, canceling them over and over until absolutely none are left.
Wait. Okay, we need to pause here because this is where the concepts get pretty wild. A negative cost cycle. That sounds like you are generating free copper wire or traveling backward in time.
It does sound impossible.
In a physical microchip, how can the cost of adding a physical detour wire be negative? You can't have negative distance.
I'm really glad you flagged that because grasping the residual graph is absolute key to understanding the whole system. The residual graph isn't describing physical space anymore.
It's not.
No, it is describing potential choices and their consequences.
Okay, I'm following.
Let's say in that sloppy first draft, you routed a signal adding a wire that cost you 50 units. In the residual graph, a forward edge represents adding a new wire, so it costs positive weight.
Makes sense.
But a backward edge represents the option of undoing a previous routing choice.
Oh, okay. So it's not a negative wire, it's a refund.
It is exactly a refund. If the algorithm sees an option to route a signal backward along an edge it's already using, that backward edge costs a negative amount.
Because you are essentially reclaiming the distance you wasted in the first draft.
Yes, you get the distance back.
So a negative cost cycle is just the algorithm realizing, hey, if I shift signal A over here and shift signal B over there, I can undo this really long, terrible wire I placed earlier and replaced it with two shorter ones. My net total cost goes down.
You've got it perfectly. It's auditing its own bad guesses.
Man, it is a continuous automated self-audit.
Right, and it keeps cashing in these refunds, shrinking the total wire length until there are no more profitable trades left to make on the entire chip.
That is brilliant in theory, but as the researcher's slide deck makes painfully clear, perfect math often falls apart when you try to force it into a software environment.
Oh, constantly. Theory is flawless, but software is messy.
Yeah, the researcher didn't just design this concept on a whiteboard. They had to code it into a Python ecosystem called diGraphX, and that is where the bug hunt began.
The transition from a theoretical whiteboard to actual Python code is a notorious graveyard for computational research.
So what went wrong first?
Well, initially, the code in the diGraphX ecosystem used a well-known method called Howard's algorithm to hunt for these negative cost refunds.
The Howard's algorithm.
Yeah. Howard's algorithm is a policy iteration method. It's generally very fast because it's greedy. It looks for the most obvious high-impact improvements first.
But the slide deck mentions Howard's algorithm had a detection gap. Why did it fail here?
Because of the sheer complexity of our microscopic skyscraper. In these incredibly dense residual graphs, you don't just have one simple negative cycle, you have dozens of them.
Overlapping each other.
Exactly. Overlapping, intertwined, sharing the exact same nodes. Because Howard's algorithm is greedy, its policy evaluation would get confused by these overlapping loops.
Oh, so it just couldn't see them.
Right. It would essentially go blind to certain complex structures. It would miss negative cycles that were sitting right there in the math.
Wow, it thought the audit was finished when there was still a bunch of wasted wire left on the chip.
It stopped early. So the chip would lock in a suboptimal routing layout, wasting precious nanoseconds, all because the software search method just wasn't thorough enough.
That's rough. So how did they fix it?
To fix this fatal blind spot, the researcher ripped out Howard's algorithm entirely and replaced it with the Bellman-Ford algorithm.
Okay, Bellman-Ford. And the source notes, Bellman-Ford runs a, quote, absolute VPass relaxation. Unpack that for us. Why does Bellman-Ford catch what Howard's missed?
So the V simply stands for the total number of vertices or nodes in the entire graph. Bellman-Ford doesn't guess, and it isn't greedy. It is an exhaustive brute force sweep.
So instead of a quick visual inspection, it's doing something much more methodical, like sending a mail carrier to walk down every single street in the city to check every single house.
That's a great way to picture it. The algorithm checks every single edge in the entire network for a potential refund.
And it does that V times.
Yes. It doesn't just do it once. It repeats that entire citywide mail route over and over, specifically V times.
But why does doing it exactly the number of vertices times magically guarantee we find the hidden cycles?
Because in any graph, The absolute longest possible path a signal can take without looping back on itself is v minus 1 edges.
Oh, okay.
By sweeping the entire network v times, the math mathematically guarantees that any hidden shortcut, any overlapping negative cycle, will have enough time to ripple through the data and expose itself.
You literally cannot hide a negative cycle from an exhaustive VPass sweep.
You really can't. The implementation they wrote, which they called Find All Neg Cycles Bruf, didn't just find one missed cycle. It could yield multiple cycles from a single exhaustive pass.
So the detection gap was completely eliminated.
Completely. Brute force beats clever guessing when perfection is on the line.
Honestly, my absolute favorite part of this whole software implementation phase is the parallel edge collision bug.
Oh, the collision bug. It's a classic.
If you are listening to this and wondering how tiny coding errors cause massive hardware failures, I mean, this is it.
It really is a classic data structure nightmare.
Walk us through this collision, because the mechanics of it really blew my mind.
We have our map, right? The algorithm finds a forward edge going from node A to node B, and also a backward edge, our refund, going from node B to node A.
Yeah.
But the software literally started eating its own map.
It did. And to understand why, you have to look at how computer memory actually stores a graph.
How does it store it?
It often uses a dictionary or a hash map. The key to looking up the data is simply the pair of connected nodes. So the algorithm writes the data for the forward edge into memory using A and B as the key.
Okay.
But when it calculates the backward edge, the refund, and tries to write that into memory, the node pair is exactly the same.
Oh, no.
The code was structured in such a way that writing the backward edge would literally overwrite the forward edge in the computer's memory bank.
The second write operation just completely erased the original path.
Yes. The negative cycle edges, the very refunds we desperately needed to optimize the chip, were just vanishing into the digital ether. The algorithm couldn't optimize the chip because its own map kept deleting itself during the audit.
Exactly.
So if your software is erasing its own roads, how do you even fix that? You obviously need both directions to calculate the refunds.
The fix the researcher implemented was incredibly elegant in its simplicity. They couldn't easily change the entire data structure of the digraphics library.
Right. That would be rewriting the whole foundation.
Exactly. So they just added a simple logic condition. When a memory collision is detected, when the software tries to overwrite an edge, always, unconditionally, keep the edge with the more negative cost.
Always prioritize the bigger refund.
Always prioritize the bigger refund. And the impact of that one tiny single-line code fix was absolutely staggering.
What happened?
By simply stopping the map from deleting the best options, the system's routing penalty plummeted. On their primary benchmark, the cost dropped from a highly suboptimal 1672 all the way down to 1108.
1672 down to 1108. That's a massive reclaim of physical wire and timing budget. It's huge. And crucially, that score of 1108 perfectly matched what they call the simplex optimum.
The simplex optimum, meaning what exactly?
It means the absolute mathematical floor. It is a state proven by linear programming that dictates you physically cannot route the system any better than that specific number.
Wow.
They hit the absolute theoretical limit of efficiency. The math was finally working flawlessly because the code stopped getting in its own way, and their random accuracy hit a perfect 80 out of 80.
So the theoretical math is optimized, and the Python software isn't erasing itself anymore? But as this deep dive shows, none of that matters if the physical silicon architecture won't cooperate.
Right, because a mathematically perfect route might be physically impossible for the hardware to actually execute.
This is where we hit the hard wall of physical engineering.
Yeah.
The researchers referred to this collision of math and physics as routing ambiguity.
Yes.
Routing ambiguity.
The slide deck breaks this down into acceptable versus unacceptable violations. Let's explore the acceptable ones first. If our newly optimized, perfectly audited graph gives a single node one incoming signal, but multiple outgoing paths, why doesn't that crash the chip? Wouldn't the electrical signal get split in half and corrupted?
It wouldn't get split because of the hard physical constraints built into the silicon that we discussed earlier.
The one-to-one hardware gate.
Exactly. The hardware itself is physically gated to only allow one functional TSV to connect to one spare. So if the math somehow offers 3 outgoing paths, the hardware doesn't try to use all 3.
What does it do?
It just arbitrarily picks one of those valid paths and ignores the others.
Oh, okay.
The signal remains whole, and it gets where it needs to go.
Yeah.
There's no ambiguity about what signal is being routed.
It's like a highway interchange. An acceptable violation is having one lane of traffic, one discrete signal that suddenly splits into three different exit ramps. The cars just have to pick one ramp, traffic keeps flowing.
Exactly. The data finds a path.
Yeah.
But an unacceptable violation is a completely different story. That happens when the mathematically perfect algorithm creates a node that has multiple incoming edges, A and D, multiple outgoing edges active at the exact same time.
Oh boy. Expanding on that highway analogy, that would be like having three separate toll booths simultaneously dumping high speed, distinct lanes of traffic into a mixing bowl with three unmarked exits.
It is high-speed chaos.
Yeah.
If that configuration was actually printed onto the physical chip, the hardware wouldn't know which incoming electrical signal belonged to which outgoing path.
The separate data streams would just collide.
They'd collide, mix, and corrupt instantly. That is true routing ambiguity, and it is a fatal error for the processor.
So, if the Bellman-Ford algorithm might naturally propose a mathematical solution that creates this highway chaos, how did the engineers stop it from being finalized?
They engineered what they call a vertex filter. Think of it as a bouncer for the algorithm.
A bouncer.
Yeah. Its sole job is to monitor the proposed negative cost cycles. If a cycle would create one of these illegal multiple in, multiple out situations, the filter just blocks it.
It just says no.
It says no. It tracks a used set of nodes and outright prevents the optimization from causing fatal ambiguity.
But true to the theme of this research, there was a bug in the bouncer too.
Of course there was.
The BFS init bug.
Yes. Remember that sloppy first draft we talked about? The initial breadth first search routing?
Right, the water expanding outward to find the closest open pipes before the cycle cancellation audit actually begins.
Well, the code was supposed to feed that initial layout into the vertex filter so the bouncer knew which nodes were already occupied.
Let me guess, it didn't.
It didn't. The filter was initialized with a completely blank slate, an empty used list.
Oh no, so the filter was effectively asleep during the first phase of the optimization.
It was completely asleep at the wheel. Because it thought every node was empty, it freely allowed the cycle cancellation algorithm to add second and third outgoing edges to nodes that were already heavily trafficked by that initial sloppy layout.
It was approving the highway chaos because it literally didn't know the toll booths were already open and flowing with traffic.
Precisely. By the time the filter's tracking caught up, the illegal multi-out connections were already hard-coded into the chip's routing plan.
So how did they wake the bouncer up?
Fixing this was straightforward but totally vital. They just had to properly initialize the filter's used memory bank with the BFS flow before starting the cycle cancellation process. Wake the bouncer up before opening the doors.
Okay, so they fix the bouncer, they fix the memory overwrites, they bring in Bellman-Ford's exhaustive mail carrier sweep. This brings us to the final results of the deck, which I actually found to be the most surprising part of the whole deep dive.
The sensitivity analysis.
Yeah, it reveals that this elaborate constraint system doesn't just magically fix every chip design. It only works under very specific Goldilocks conditions.
The physical architecture dictates everything. The effectiveness of this entire algorithmic dance is completely dependent on the edge density of the graph, which they denote with the Greek letter eta.
Eta, meaning how crowded the microscopic skyscraper is with potential elevator shafts.
Correct. Through pretty extensive testing, they found that the constraint filter only successfully improves the routing in a narrow window where eta is between 1.5 and 1.7.
Because let's look at why. What happens if the graph is too dense? Say eta equals 1.8.
If it's 1.8, there are so many available routing options, so many spare elevators, that the natural algorithm doesn't really create traffic jams. There are no unacceptable violations to fix in the first place.
Too many elevators, no bottlenecks.
Exactly. But on the other end of the spectrum, if the graph is too sparse, if eta equals 1.3, there are so few spare elevators that when the filter identifies an illegal multiple in, multiple out highway pileup, there are simply no safe back roads left to take.
So the filter correctly blocks the bad route, but the chip is still stuck because there are literally no alternatives.
Right. The Goldilocks zone of 1.5 to 1.7 is where the network is just constrained enough to need the filter, but flexible enough to actually use it.
It's fascinating because it means if you are holding a high-end device right now, its internal architecture was likely designed to sit specifically inside that density window just so these auto-healing algorithms have room to breathe.
Exactly. It's a very intentional design.
The source also mentions the physical distribution of the faulty TSVs plays a huge role.
It changes the outcome entirely. They tested this algorithm against uniform distributions, what they call VDC graphs, where faults are spread out perfectly evenly and against completely random clustered distributions.
Why does clustering matter so much?
Well, because manufacturing defects aren't polite.
What do you mean?
A speck of microscopic dust hitting a silicon wafer doesn't just take out one TSV every millimeter. It takes out a clustered neighborhood all at once.
Ah, okay.
What they found was that on naturally clean, uniformly distributed VDC graphs, forcing this complex constraint system actually degraded the chip's performance. The natural flow was already efficient enough.
So the bouncer was just getting in the way of a calm room.
Yes. Yeah. But the algorithm absolutely shined on the clustered distributions. When faults happen in messy clumps,
Yeah.
they create massive natural bottlenecks.
And that is exactly where this complex, cycle-canceling, auto-healing algorithm proves its immense worth.
Untangling the clumped traffic jams that would otherwise kill the processor.
When you step back and look at the whole picture, optimizing these microscopic skyscrapers is this incredibly delicate, high-wire act. You need brilliant, high-level mathematical concepts like Bellman-Ford brute force sweeps to find these theoretical refunds.
Right.
But you have to constantly wrestle that pure math against the stubborn physical realities of hardware constraints and the mundane, messy realities of a Python script accidentally overwriting its own dictionary memory.
It really is a masterclass in interdisciplinary engineering.
Yeah.
And, it matters to all of us because this invisible, highly complex, automated self-healing is happening constantly behind the screens of our lives.
Yeah.
It is the silent mechanism that allows the increasingly dense vertical technology in our smartphones, our laptops, and the massive data center servers powering the global internet to function reliably. Without algorithms dynamically hunting down bugs and routing around physical damage in milliseconds, our modern tech infrastructure would be incredibly fragile.
And that leads to a thought that I just can't shake after reading the source material.
Hmm.
We have just spent this entire deep dive exploring how microscopic microchips use brilliant algorithms to optimally reroute around their own physical damage in real time.
Yeah.
They are constantly auditing their own networks, finding negative cost refunds, and prioritizing traffic away from cluster damage. It makes you wonder, how long until we scale this up?
Scale it up.
Yeah. How long until we apply these exact algorithmic self-healing networks to our macro physical infrastructure? Imagine a national power grid or a global supply chain automatically detecting a downed line or a blocked shipping port and instantly calculating a Bellman-Ford cycle cancellation to reroute electricity or cargo perfectly seamlessly before any human even realizes there was a problem.
That's an incredible thought.
If the skyscrapers in our pockets can already do it, maybe our actual cities are next.